Hi dear students, welcome back all of you to the physics online class. So in the previous video you learnt the derivation of the interference fringe width, yes, and there in that class we discussed how the fringe width beta can be derived, and its expression is beta is equal to lambda d by d. What is the beta here? Beta is the fringe width. Fringe width means what? It is the distance between any two successive bright fringes or any two successive dark fringes. Yes, and diagrammatically also I have shown you the distance. If I consider here in the NCERT text they have given a beautiful diagram. They have considered there is a one source of the light, let us call it is a source S here, and in another screen it is given that there from the single source or the single slit we have derived the two coherent sources. From this only we have derived the two coherent sources, that is a slit 1 here and a slit 2 here. We used that as a S1 and S2, and the light waves which are coming from the S1 and S2, they superimpose each other. So with the different phases or constant phase difference. If the wave fronts or the waves coming from the S1 and S2, they have even integral multiple of the pi. If, as I told you early, the constructive interference, for that the phase difference should be equal to even integral multiple of the pi, and if it is so, that means here we get the constructive interference, that is nothing but the bright fringes are obtained here. So this pointer tells that if the waves are coming from the two coherent sources S1 and S2, if they have the zero phase difference or the phase difference is equal to even integral multiple of the 2n pi, then here remember they can form the bright fringe. I am showing here the bright fringes, right. So whatever I am shading, that is a bright, and its next will be the dark. Okay. These are the bright fringes. Okay. So this diagram giving me these all are considered to be the bright fringes, and where I have not shaded that part indicates the dark fringes. How the bright fringes are formed here? When the phase between them is equal to even integral multiple of the pi, or the what I can say, the path difference between them is equal to integral multiple of the lambda or even integral multiple of the lambda by 2. Then such a waves can produce the bright fringes on the screen. It is a screen which we used, and that is kept at a distance capital D, isn't it? Yes. Then how the dark fringes are produced here? The dark fringes are produced if the phase difference, the waves coming from the S1 and S2 have the phase difference of 2n plus 1 pi, that is the odd integral multiple of the pi is there, or the path difference delta is equal to odd integral multiple of the lambda by 2. If any one case is valid here or applicable, then such a waves can produce me the either the dark fringe. Yes. So how they are performed? With the help of the superposition here. And see dear students, by the interference of the light, what fringes we are obtaining? We are obtaining alternative bright and the dark fringes. But in the experiment, remember the central point O is considered to be the bright only. See, already in the previous class I have shown you the diagram while deriving beta is equal to lambda d by d. Here we taken that S1, S2 are the two sources. They are separated with a small distance d here, okay, and the screen was kept here, and here I used one point called O here. Can you remember this? It was a point. See dear student, this point O is where the bright fringe only formed. Why? Because the distance of the O from the source S1 and S2 is equidistance here, equidistance, and also the waves which are reaching the point O, they have a zero phase difference or constant phase only. Hence, when they superimpose at that point we get the bright fringe. So, remember, in the interference of the light, the central which fringe will be there? Bright fringe only will be obtained. Am I clear? Yes. And related to the intensity curve, let us discuss now. How will be the intensity curve? The intensity curve for this alternative bright and dark fringe we can represent here. When you plot the intensity graph, remember dear students, the intensity of all bright fringes remains the same only, and for all dark fringe also remains the same. Yes. So, this will be the intensity curve, and this I can consider as the central bright fringe. This is a central bright fringe. Yes, and this is followed by the alternative dark fringes here, which the trough is showing, trough, these are the troughs. The troughs are showing the dark fringes and the crusts are showing the bright fringes. Okay. So, then see, by seeing this, what you can feel by observing this intensity curve, you can determine that. So, the intensity of all the bright fringes remains the same in the interference of the light, and also the intensity of the all dark fringes remains the same in the interference of the light. Yes. So, that only the point we can derive from this graph here. Okay. Yes. Then let us discuss about what the fringe width explains here. Fringe width shows that the fringe width of the interference band that depends, see, sometime for a 1 mark or the competitive purpose there may be a question, name the quantity on which the fringe width depends directly. Yes. So, then there also you can have this answer, or sometime there will be a question, twisted question. If the wavelength of the incident light increases, what happens to the fringe width formed by interference light? Yes, what happens here? That can all be, everything is answered with the help of this formula only. This formula shows me that the fringe width beta is directly depends on the wavelength of the light, isn't it? See here, beta is equal to lambda d by d. So, the fringe width is directly depends on the wavelength of the light. That means, if the wavelength of the light is increased, the fringe width also increases. For example, let us take lambda is equal to 400 nanometer. Yes, I have taken first wavelength as a lambda 1, I can say, that is equal to 400 nanometer. Then for this, what will be my beta? Just I take a general example. I got that the beta, the fringe width, that is equal to 3 millimeter, let us assume. Then if I take the second light which is having a wavelength of 550 nanometer, let us assume, then definitely tell me what will be the beta value, whether it is a more than 3 or less than 3. It is more than 3 only, maybe nearly the answer may come, that is beta is equal to 4.5 millimeter. Why? Because the beta value directly depends on the wavelength of the light used. Right. If the wavelength increases, the fringe width beta also increases. Remember dear students, these are the factors on which the wavelength, the fringe width of the interference band depends, what I am discussing now. Yes? Okay. Then the second point is, beta directly depends on the capital D. What is the capital D? It is the distance between screen and the coherent sources. You have seen the distance there. Capital D is the distance between the screen and the coherent sources, or screen and the slits, double slits there. Yes, and see, if you go on increasing, assume here are the two slits, S1 and S2, and this is a screen. Then if you go on increasing the screen and this distance, what happens there? The fringe width after the interference of the light, what fringes are formed, they appear bigger in a size because we are increasing the distance capital D here. Yes, if you bring the screen very near to the slit, then what you observe there? There the fringes which are formed after the interference of the light, they appear to very thin in a size, because if the capital D decreases, the fringe width also decreases, because they are directly proportional to each other. I hope this point is clear dear students, right? Yes. Then the last point is beta inversely depend on the small d here, inversely depends on the small d. What is the small d? Small d is the distance or the separation between the two coherent sources. Yes, in the diagram you have seen that this is a S1 and this is a source S2. These two are acting like a coherent sources, isn't it? Yes. If this distance is decreased, tell me dear students, first of all you should know what is the inverse relation. In the inverse relation, if one quantity is decreased, the other should be increased. Remember. So here also same relation happens. If the distance between the two slits decreases, then the fringe width increases. What happens there? Fringe width increases. Or, so you can take vice versa. If the distance between the two slits increases, distance is increasing, then here the fringe width will decrease. So like this, you can say that the fringe width, how can you increase or how can you, so double or whatever, how can you change the fringe width of interference bands? First one, you can change it directly by using the wavelength, light of the higher wavelength, or by increasing distance between screen and the slits, or by decreasing the distance between the two coherent sources. Okay dear students? Yes. So this is what the points we wanted to discuss in the interference. Yes, see dear students, this is a one phenomena of the light by considering the wave nature. Yes. So in the beginning we discussed how the wave optics started, and when the point comes to interference of the light, there we started that the modification in the intensity of the light or the redistribution of the intensity of the light when a two or more light waves superimpose each other in the same direction, isn't it? Then in the interference again we classified that as a two. One is a constructive and another one is a destructive. Constructive means where you have seen there is increase in the intensity. Destructive means there decrease in the intensity. Yes, and by the superposition principle also we discussed that point, right. Then next we moved the theory of the interference, that is giving a beautiful meaning, that is if the amplitude of the resultant wave is increasing, definitely its intensity also increasing, isn't it? And with the help of that theory of the light only, we particularly talked how the constructive interference of the light will take place and how the destructive. Yes, there particularly we discussed the conditions, that is a phase difference pi should be equal to even integral multiple of pi, or path should be equal to even integral multiple of lambda by 2, that gives me the constructive. Just now I told that also, isn't it? And if it is the odd integral multiple of pi, or the path difference is odd integral multiple of lambda by 2, that gives me the destructive interference. Okay, and that constructive and destructive only nothing but constructive means the bright fringes, destructive means the dark fringes. Yes, and that are formed. And the very important the derivation for the 5 marks is derivation of the fringe width by using Young's double slit experiment. What the Thomas Young said there in his experiment, he used a source of the light, and from the single source he taken the two waves and passed through the two slits, that slits only acting like a coherent sources. Yes, and after the slits what the waves are continuously emitting, they only superimposed each other, and when they superimposed, according to the change in their phase or the path difference, they formed the alternative bright and dark fringes on the screen there. And compulsorily you have to keep in mind that the central O point is the bright fringe only. Yes, why? Because the continuous waves which are coming there, they are superimposed with the 0 or the constant phase difference. Hence it gives me the central bright only. And just now I shown how the intensity curve will shown in the case of interference of the light. Yes, and next one, the beta is equal to lambda d by d, that is derived with the help of the Young's double slit experiment. And from that experiment it is clear that the fringe width beta is equal to lambda d by d. And now the point came on what factor the fringe width beta depends. Yes, and the fringe width beta can be increased by increasing wavelength, because it is directly depends on that. It can be increased by increasing distance between the sources and the slits there, slit and the screen here. And if the distance between the sources is decreased, then the fringe width increases, because it is related inversely with the distance small d here. Okay, and these are all the points related to the interference of the light. But here the 2 points you have to concentrate more is the first one, which principle is involved in the interference of the light? The superimposition principle is involved. How many minimum coherent sources are required to form the interference of the light? 2 minimum coherent sources are required to form the interference of the light. And the day to day life where you are observing the interference of the light, the thin films, thin color films which is formed when oil spill over the surface of the water, that is because of the interference of the light. The same thing you can observe when oil spill over the tar road, there also the thin color films can be formed, that is because of the interference of the light. And if you come with the experiment, there the Newton rings are formed. That is also interference of light. Yes, dear students, so today again we discuss the next phenomenon of the light, that is the diffraction of the light. See, up to now the interference is very clear to all of you, and there you have to focus on the, as I told, on the derivation beta is equal to lambda d by d only. Yes, and see, after the interference, what the bands are you are getting, they are only called as the fringes, and their alternative bright and dark fringes will be there. The distance between any two consecutive bright or dark only called as fringe width. Yes, see dear students, the next phenomena, diffraction of the light. So how the diffraction and what is the meaning of the diffraction? Actually, this is a light nature that indicates a wave nature of the light. When a light enters through the slits, you can observe that the light is bending around the edges of the obstacle, and after bending that, it will enter into the geometrical shadow. If you see the door, the light coming from the door, and around the edges of the door, the light will bend there. And due to that bending only, where it will enter? It enters to the geometrical shadow region. And there you can see that when the light around bending that around the edges of the obstacle, there you can observe there is a formation of, there is a change in the intensity of the light. Yes, under that shadow you can see there is a intensity, change in the intensity. So therefore, the diffraction of the light means what happens here actually? This is a phenomenon of bending of the light rays, bending of the light rays around the edges of an obstacle, around the edges of an obstacle, and entering into the geometrical shadow region. Entering into the geometrical shadow, such a phenomenon we call it as the diffraction of the light. Yes, and here also the wave nature is so identified. And the next one here, actually, if the ray is, as you consider, see dear students, all the time we may not observe the diffraction of the light. So it can be observable when the wavelength of the incident light is almost sensitive to our human eye. Yes, if our eye is able to see that wavelength, then only the formation or the bending of the light and its effect can be seen. And one general good example for the diffraction of the light is what? The formation of colors on the CD drive. Have you seen CD cassettes? So ಹಾಡನ್ನು ಪ್ಲೇ ಮಾಡ್ಬೇಕಂತ CDsಗಳನ್ನು ನೋಡ್ತೀವಲ್ರಿ, ಅದನ್ನ ನೋಡ್ರಿ ಲೈಟಿಗೆ ಹಿಡ್ತೀವಿ ಅಂದ್ರೆ ಕಲರ್ ಫಾರ್ಮ್ ಆಗೋದು. It is because of the diffraction of the light only. Yes, and that effect is because of diffraction. And when the light need to undergo the diffraction, remember the size of the obstacle is considered to the wavelength, it should be the smaller. So then only you can observe the diffraction of the light. Yes, and usually how the theory of the diffraction started? There the scientist called Fresnel and the Fraunhofer. So these scientists worked on the diffraction of the light, and in their studies both used different sources and both assumed differently only, but final result is diffraction of the light only. Then according to Fresnel, what? Fresnel told that the light waves which are using are either in a spherical or cylindrical in a shape. Fresnel, his explanation or in his diffraction experiment, he used the spherical or the cylindrical wavefront to observe the diffraction. And one more thing he had done, he kept the source of the light and the screen at the finite distance there. Yes, and but when you come with the Fraunhofer used the plane wavefront for his experiment. That only light only used, but they are plane wavefront. and he also taken the source and the screen at an infinite distance. Yes, by that only he started to know the experiment of the diffraction of the light. Then later we also, for the further studies, we are using the Fraunhofer diffraction only, where we assume that the source is kept at a infinity and screen at a particular, that means distance between source and the screen is infinite, and what waves are coming from the source, we assume that they are plane wavefronts only. Yes, and serious one, this much enough, and further things about how the diffraction of light takes place through the single slit and its theory, and how the secondary maximas and secondary minimas will be formed during the diffraction of the light and its intensity curve. Everything we will discuss in the next video. If any queries, you can send me the questions. Thank you for watching video.